Dear friends, we're going to discuss the various electrophilic aromatic substitution reactions of benzene as a part 3 of this series. Let us understand what is electrophilic aromatic substitution and also discuss the 5 different typical reactions of benzene under this category. So under electrophilic aromatic substitution, first let us discuss the reactivity of benzene as compared to its non-aromatic cyclohexatriene. Under KMnO4 oxidation conditions, benzene gives no reaction. Same happens for the addition of halogens, whether it is bromine, chlorine or HI, and same happens with the addition of hydrogen, that is the hydrogenation under catalytic conditions, which is quite sluggish. So in short, the inherent stability and the aromaticity of benzene resists addition reactions in general. Instead, it prefers the electrophilic substitution reactions. Let us understand the basic thing, what is substitution and what is addition. I give you a simple example. When you come to the classroom in the morning, your classroom is empty. Slowly when you fill up all the benches, that is addition reaction. Now there are certain students who have missed the first lecture due to various reasons. Well, there are certain students who don't want to attend the second lecture, but the first category of students, some of them, they want to attend the second lecture. So some people come in and some people go out. That means the first lecture attending few students who have left have been substituted with the new students who wish to attend the second lecture. So I think this is a very simple and practical example which describes what is addition and what is substitution. There is another third type of reaction, elimination. Very simple practical example is when all your theory classes are over, everybody vacates the classroom, that is elimination reaction. I think this way it is better to remember. So in place of addition, benzene prefers electrophilic aromatic substitution because of its very strong aromaticity and stability. And there are 5 different types of reactions: nitration, halogenation, sulfonation, Friedelcrafts Acylation, Friedelcrafts Acylation, which we are going to discuss. So benzene with nitration gives you nitrobenzene, benzene with chlorine gives you chlorobenzene, with bromine gives you bromobenzene, with sulfuric acid or fuming sulfuric acid it gives you benzene sulfonic acid, with alkyl halides gives you alkyl benzenes, and with acyl halides it gives you acyl benzenes. See, the beauty of this reaction is it is not an addition reaction, but one H has been replaced with nitro here, with chloro here, with bromo here, with SO3 here, and with alkyl group here, with acyl group here. So these are substitution reactions. And why benzene undergoes? Because it doesn't want addition reaction, because addition will destroy its aromaticity and its stability. Therefore, it readily undergoes substitution reaction where the aromaticity and the ring system is preserved. Let us see it in much details. Just recollect the benzene ring system, which is a flat ring system, and over and above the ring system there is uniformly distributed pi electron clouds. So due to these pi electron clouds which are rich in electron, benzene above and below its ring system has a negative charge, and therefore it does not invite electrons. Electrons are rather repelled out. So what benzene attracts is electron deficient or electron loving systems, or in other words electrophiles, which come and get attached. Now first step is the formation of a carbonium ion, and this carbonium ion is the result of the, what you can say, uh, addition of the electrophile. So first the electrophile attacks the benzene to form an intermediate carbonium ion, which is also called as a benzonium ion or a pi complex, and this is the most important step which requires activation, or it is the rate determining state. So the electrophile is attracted by the pi cloud, it gets attached, and this carbon, particular carbon, has an additional valency, so it is positively charged, it is a carbonium ion. Next step is very fast. The conjugate base of that electrophile, which is roaming around, leads to the abstraction of the proton and thereby stabilizes the product. Okay, see, this conjugate base has abstracted the proton and it stabilizes the product. So the first step is the rate determining step because it requires activation. See, this is the uniformly distributed pi electron clouds above and below the benzene ring system, which are the source of negative charge to which the electrophiles get attracted. First is the nitration. It is a reaction between benzene and nitric acid, and the electrophile is the positively charged NO2, that is a nitronium ion, and it displaces the edge of the benzene. These are the 7 different conditions for nitration, that is nitric acid concentrated, or a combination of concentrated nitric acid and sulfuric acid, fuming nitric acid in concentrated sulfuric acid, or both the acids fuming. Also acyl nitrates, nitronium salts, nitronium pentoxide in carbon tetrachloride. Most preferred condition is a combination of nitric acid and sulfuric acid. Sulfuric acid serves as a hygroscopic or dehydrating agent because in all these reactions water molecule is formed which dilutes the reaction medium and makes the reaction reversible. So sulfuric acid traps this oxygen, water molecule, and helps to take the reaction to forward direction or completion. So this is the simple reaction. You can see one hydrogen has been replaced with NO2 group and water is formed. Let us see the mechanism. First, the electrophile is formed by the reaction between nitric acid and sulfuric acid. So the nitronium ion is formed. This nitronium ion in the first step basically gets attached to the benzene ring to form the carbonium ion, and its conjugate base, that is HSO4 minus or hydrogen sulfate, abstracts the proton. This is a rapid step. You get nitrobenzene. Second type of reaction is halogenation. It is a displacement of the H of benzene with a positively charged halogen, which is called as a halonium ion. For the bromine, it is bromonium ion. Chlorine, it is chloronium ion. So benzene reacts with chlorine or bromine, and it requires a catalyst. Catalyst is either AlCl3 aluminum chloride or FeCl3, ferric chloride. Ferric chloride, if you just use iron filings uh, in the presence and you take a chlorine gas or bromine, in situ ferric chloride or bromide is formed, and both ferric chloride, bromide as well as AlCl3 are Lewis acids. The role of these Lewis acids is to abstract the chloride from the chlorine and generate the chloronium, or same thing with bromine to give bromonium. They also have a second step, that is the conjugate base of this AlCl3 or FeCl3, that is AlCl4 or FeCl4, is readily abstracting the proton and driving the reaction to completion, which is explained in the next slide. Same thing here, reaction with bromine. See, now why this chlorine is broken into two different poles or two differently charged species, positive and negative? There are two explanations. This is very important. When the chlorine molecule approaches the benzene ring, the pi cloud, which is in the vicinity of this approaching molecule, pushes the electron pair of chlorine towards a distance. So one chlorine gets more of these electrons, becomes partially negatively charged, and the chlorine which is facing the benzene becomes partially positive charge, and then they break into chloronium and chloride. And this is further facilitated by the catalyst, that is the Lewis acids, AlCl3 or FeCl3. So let us see, this is the mechanism. AlCl3 is further facilitating the removal of the chloride and forms AlCl4, and so the chloronium gets attached, and in the second case the conjugate base AlCl4 abstracts the proton to help the formation of chlorobenzene. Sulfonation on similar lines. Basically, there are two conditions employed. One is benzene is heated for a prolonged time with concentrated sulfuric acid, but this reaction seldom goes to completion. As I told you, water molecule is formed and it gets stuck to an equilibrium. To make it more efficient, sulfuric acid is saturated with sulfur trioxide, which is fuming sulfuric acid. It requires very less temperature of 40 degrees centigrade, and it hardly takes half an hour to drive the reaction to completion. As I told you, water molecule is formed, but if you use fuming sulfuric acid, this reaction is faster. Here you don't use any catalyst, because what happens is the attached sulfuryl group has one oxygen which is negatively charged, and there is intramolecular abstraction of the proton, and it forms SO3H. So the product is benzene sulfonic acid. Fourth reaction is Friedelcrafts Acylation. Now under Friedelcrafts Acylation, the proton is substituted with a positively charged alkyl group which acts as an electrophile. Therefore, a benzene is treated with a chloroalkane like chloromethane or chloroethane in presence of aluminum chloride as a catalyst. Aluminum chloride will abstract the chloro or bromo to generate the electrophilic alkyl group positively charged, and therefore this will get attached to the benzene, okay, and then the AlCl4 will abstract the proton. This is the generation of the methyl electrophile positively charged and the conjugate base of AlCl4. The first step, this methyl electrophile will get attached to the benzene to form the carbonium ion, and then AlCl4 rapidly will abstract the proton to give you methyl benzene. Similar type of reaction is Friedelcrafts Acylation. Only difference is the species is, instead of alkyl group, it is an alkenoyl group or acyl group. So acylium ion is the electrophile which replaces one hydrogen. So when benzene is treated with ethanoyl chloride, or simple words acetyl chloride, in presence of aluminum chloride, a ketone called as phenylethanone, or simple words acetophenone, is formed. And aluminum chloride is, of course, as usual, the catalyst. And this is the mechanism. The acylium ion is attached to form a carbonium ion. And the conjugate base of AlCl4 will remove this, what you can say, the acylium ion. So you can see the reaction mechanism. Okay, fine. There are some questions one can note down and try to solve, so your things can be revised. You have to explain the mechanism of all these reactions, their reaction conditions. So also the generation of the electrophiles, whether it is nitration, whether it is Friedelcrafts alkylation, acylation, halogenations, etc. So thank you friends, thank you very much.